Great. We can get started with today's webinar. A very warm welcome to all the attendees from phase two, that is the ideation phase of the India Smart Protein Innovation Challenge. And like you all know, this is our webinar number 8. Cannot believe it, right? Just like a week ago, we started with our first kickoff webinar a couple of weeks ago. And then in the last week, we had a flurry of webinars coming your way. And I'm very thankful for all of you that you take the time out to attend it live and go back and discuss with your teammates about the things that you've learned. That is really our motive here, and I'm really glad that you're playing along. So today's topic is basically end product optimization and white space opportunities along the smart protein value chain. And like yesterday, Siddharth Bhide, who's a science and technology specialist. I'm just going to quickly introduce Siddharth for people who were not there with us yesterday. Siddharth basically leads the science and technology function at GFI India and is currently focused on the plant-based side of things. So that's his expertise, and he comes with a background in food science and technology. That was his undergraduate at Osmania University, after which he went to Rutgers University in New Jersey for his master's, and then spent a considerable amount of time in Silicon Valley at just 3 years thinking about the plant-based egg category and multiple other smart protein and alternative protein categories. And he's also had experience with General Mills in the past, and he brings a lot of valuable experience in scale up, new product development, understanding the science and technology behind multiple areas that are focused in this challenge, plant-based meat, eggs, dairy, seafood, and powering plant solutions. So having said that, Siddharth, would you like to begin with today's session? Just like yesterday, please feel free to submit your questions based on the section that we are discussing as and when they occur you, so that people can upvote and you also get time to add context and you don't forget about it later. And we are going to have a small break after the first bit so that we can cover some questions, maybe for 5-10 minutes, then cover the second part of the deck, and then we'll open it up for half hour or 40 minutes of Q&A. Thank you so much for joining us today, and let's get started with this exciting session.
Thank you, Shardul, and welcome everyone for today's session on understanding how do you mix all of the ingredients together and how do you optimize to create a final plant-based meat product having the right texture and right flavor as its animal-based counterpart. So in today's presentation, we'll be focusing on end product optimization, and in that we'll be focusing on extrusion technology because that is the most commercial technology available to make plant-based meat products. And I'll also be introducing some other technologies like shear cell technology, 3D printing, spinning, freeze texturization, etc., so that you also know about it, and feel free to read up more on it. But that won't be the focus of this presentation today. Then we'll be walking through a process flow, which can be used to create plant-based meat products. And again, they could be restructured products or whole muscle products, which I'll be talking about in the slides too. We'll be touching a bit on nutrition part, like how can you increase your nutrition of your plant-based meat product from a macro and micronutrient standpoint. And we'll be ending the presentation talking about the white space opportunities that exist across the plant-based meat value chain. So where all can you have your projects in so that in the end it contributes to delivering a plant-based meat product. So again, I always like to start off with a product slide because essentially this is what you're trying to make. And again, Impossible Burger, Beyond Burger, these are path breakers in this domain. So this is your Impossible Burger. Again, a lot of ingredients, but each ingredient has a specific role to play. And yesterday we spoke in depth about how do you really make, the soy protein concentrate or soy protein isolate or potato protein. And we also touched a bit on, why are fats used, why are binders used, why are different flavors, colorants, and preservatives used, etc. Today, what we are going to be talking about is the extrusion technology that is used to actually create a low moisture extrudate from, in this case, soy protein concentrate, soy protein isolate, and potato protein, as you can see on the bottom of the screen. So starting off with just the type of extrudates that can be used in creating plant-based meat products, what you saw on the screen and what Impossible used was what we call low moisture extrudate, where the extrusion moisture content is less than 30%. And typically these type of extrudates are used to make restructured products, or in India, you could think about it like keema-like products, right? So where, you have your TVP or low moisture extrudate that you get, it is in dry form. You hydrate it using water, fats, broths, and then you cook it or you freeze it depending upon if your product is ready to cook or ready to eat. Now, low moisture extrudates have been available for a long time. So your soya nuggets, what you get out in the market, are also a form of low moisture extrudates. But then again, these extrudates don't have the right texture that a plant-based meat product has. So that's why we call them plant-based meat 1.0, something that has existed for a long time. But then, as you saw, Impossible did not use soya protein concentrate alone, right? It used a blend of concentrate, isolate. It also added potato protein. And this was for a reason, to get the right textural properties. So these are what we know call low moisture extrudates, or TVP, or plant-based meat 2.0. And that is what is going to be the focus of this presentation and of this sector. The second type of extrusion method or extrudate is known as high moisture extrudates, where the moisture content is greater than 40% typically. And this is a technology that is relatively new and has been, developed and optimized just over the past few years. And the difference between this technology, as will become obvious in the coming slides, is that you actually get proper, muscular striata that you see in animal-based meat products, and that is the beauty of this technology. But then again, it is also novel, and people are still trying to optimize the equipment, the processing parameters, etc. So Impossible Foods is a company, which has low moisture extrudates in their portfolio, and you can see that on the screen. The products what they make are also minced products and not really whole muscle products. Similarly, Maple Leaf Foods, which is a company based out of Canada, also uses low moisture extrudates to make their products. And again, their products consist of, as you may expect, like sausages, patties, ground products, etc., which use the minced format. When it comes to high moisture extrusion, this is a company called Oja, based out of Netherlands, and it uses high moisture extrusion technology to make plant-based chicken. And as you can see on the screen to your right side, you can actually see all those muscular striata. And you might think this is a actual chicken product, but it's not. It's a plant-based chicken product. Similarly, a company called Good Catch is another company making using high moisture extrusion technology to make plant-based seafood. So what I'm going to do here is I'm going to show you two videos, one on low moisture extrusion technology and one on high moisture extrusion technology, so that it becomes more interactive after that. So 1 second, I'm going to stop sharing. Share my screen again. Are you guys able to see my screen?
Yes.
Okay, I'm going to play a video now. So something for you to just watch. And this is on how low moisture extrudate is made.
Make it full screen.
So you can see the ingredients being mixed here into the hopper. Then they go inside this extruder, and as you can see, it's a pretty big equipment. And then it comes out in the form of dried extrudates. And that's how it looks. Now, so that was low moisture extrusion technology. Now let's watch a video on high moisture extrusion technology and how did they use that high moisture extrudate to make their final product. This is a company called Coperion. You can check them out. Again, state-of-the-art extrusion makers. And it's a pretty, sophisticated equipment. You can see that, it has an electronic dashboard, state-of-the-art technology being used. That's your high moisture extrudate coming out. And you can see it's very different from low moisture extrudate. And it has got that muscular, fibers inside it. You can change your processing parameters for different product structures. You see, this is like more dense than the other product. You can add colors and flavors to your process. So you can see how the color of the product is changing. So if you add a reddish color, to get a more meat-like color, this is what you can do. And you can again see those fibers that you wish to see in your final product. And this is how he's going to be using it now. You can cook it to make it a ready to eat product at home, or you could just sell it as is and ask consumers to cook it. I think over here he's going to be making tacos out of it. So you can use it for this application, or for a more Indian application. You can probably put it in a gravy or something, or put batter on it and make chicken tikka, chicken Manchurian, etc. That's your final product. Cool. I'm going to share my presentation again. So were the videos clear, Shardul?
Yes, absolutely.
Okay, perfect. So now that you guys have got a real life, video on how low moisture extrusion takes place and how high moisture extrusion takes place, let's walk through the details now. So what really happened in these proteins, and especially demonstrated in the first video, is you saw the soy protein isolate pouring into the hopper, right? And then coming out as extrudates. What really happened is the denaturation of proteins. So plant proteins, which are globular in nature, essentially got converted into fibrillar proteins because of a combination of temperature and pressure acting on them. And this is what you saw. This is what we spoke about. This is called texturization. What we saw here was extrusion technology of texturization. But then, just in general, there are two approaches you can take: a bottom up strategy or a top down strategy. With extrusion, it builds the individual fibers and the collated fibers together. So that's why we call it top down fibers, top down strategy. But there are also some technologies that we'll be discussing later in which use a bottom up strategy. And a good example is spinning technology, wherein you develop individual fibers and then you kind of collate them together to get the finer fibrous structure. Extrusion cooking, again, this is just the definition. And here is a flowchart of how extrusion can be used. I think what is important over here is that your number 4 is the feeder, and you have to be very precise in your feeder. So a lot of you who have done experiments on a lab scale, you measure your ingredients, right, in a weigh boat or something, and you keep adding and you make these products. But imagine when you're making tons and tons of extrudates, you are not going to be able to literally weigh everything. So you need to have these automated systems called feeders, and typically it's a lot of technology even in this, because depending upon the viscosity of your material, density of your material, you need to set different parameters in these feeders so that it feeds the right amount what you want inside your extruder. And then you have your extruder after that. And then what's important is number 7, if you can see on the screen, which is the cooling die. And this cooling die is very important because this is what really differentiates high moisture extrusion technology from low moisture extrusion technology. And we'll be talking about this in the coming slides, because it really aligns all the fibers together. That's why you see that fibrillar structure. Extrusion cooking, again, these are the basics of the extruder. So you have your hopper from where you fill your material in. Then you have your barrel inside which the screw is housed. Then you have your die at the end, which helps in cutting the material and shaping the material. You have a rotating knife sometimes to break your extrudate at the desired length. Devices for heating or cooling the barrel, because all of this is happening because of a combination of temperature and pressure. So you can apply temperature at different stages of the barrel, and again, different temperatures that are applied lead to different types of final products. Ports for injection of steam, measurement instruments, because you constantly need to monitor the temperature of the product or the moisture of the product or any other parameters. So all this is very important. And here is a real life extruder from Washington State University's pilot plant. And you can see a schematic of it at the top too. So it's a pretty big equipment. And this is something you have to think to, right? Because if you're working with, say, a plant-based dairy or something, you can actually make 1 liter of product and test if it is working or not working, and then change your formulation again. But with an extruder, you need at least a very high amount of minimum quantity just to make 1 batch. So if you are a startup who doesn't have a lot of funds to invest in, just like raw material purchase, etc. This could be a bottleneck for you. Whereas with a plant-based dairy or plant-based tech product, you could still do a lot of iterations with a smaller batch. They say extrusion is a art as much of a science it is, because it's just so many parameters that blend in making a final extrusion product. When it comes to equipment related parameters, it's the screw configuration. You can change the flight length. So when you saw the screw, so let me go back to this, right? So when you saw the screw, you actually saw that the screw is composed of a lot of flights. So I can actually change the length of these, or the distance between the flights, and my final product quality would change. I can change the channel depth, which is the distance between the barrel and the screw, and my final product quality would change. I can change the helix angle, and then my final product quality would change. And I think it's coming up later. Uh, so we have that. We also have barrel temperature, which you can change, and your final product quality will change. You can change your die configuration to get a different sort of product at the end. In terms of ingredients, also ingredients have a huge role to play. Your lipids, you don't want to have too much of fat, because then it's going to cause slipping, and it's never going to generate the amount of heat that you need for denaturation. At the same time, you don't want absolutely no fat, because then that is going to create a lot of friction, and your extruder could just like get clogged because of it. Starches and fibers, same thing. They'll change your final product quality, and even your source of protein, at what temperature it denatures, etc., is also going to change your final product quality. So imagine running an extruder with so many variables. So that's why they say that it's a science, but it's also an art. You just need to understand the extruder. And this is what I was talking about. Your sugars undergo Maillard Browning reaction. Your starches, essentially a phase transition. Your proteins, they denature. Your lipids, they typically reduce the friction, may not be ideal, but at the same time, you still need to have some amount of them. Fibers, again, not preferred in formulation, because they absorb a lot of water, in some way also cause slipping. There are two types of extruders. There is a single screw extruder, and as the name suggests, it just has one screw inside the barrel, and it's less expensive of an equipment. So people who are focusing on creating a low moisture extrudate product here, you can think about this, because it can still make low moisture extrudate products. Whereas people who are going ahead with high moisture extrusion technology, you should consider a twin screw extruder, because it has two screws inside, and it's just much more robust, and you can create a lot more product structures using it, but it's also more expensive. So now we are going to just talk about a paper, because I wanted to show how different variables of extrusion can change your final product characteristics. And what has been done in this paper is that they have actually, so there are three parameters they are working with. They are doing low moisture extrusion, high moisture extrusion, and then comparing the final product. They are changing the screw speed and comparing the final product, and then they are doing an experiment without wheat gluten and with wheat gluten, and checking the final product. And again, a twin screw extruder was used because you wanted to make a high moisture extrusion product too. So let's walk through the results. And this is what I was saying, right? So it's not like you need to have just one configuration of screw throughout your extruder. Look at how they have changed the distance between the flights. If you are just looking at low moisture extrusion at the top, it starts off with a low distance between flight, then it increases, then again it decreases. Then they have actually changed the helix angle at some point. And this is also complex, right? Imagine me like, changing some part of the extruder, and again, that is going to impact my final product quality. And with high moisture extrusion cooking setup, you'll see this long slit cooling die, which is very important, again, to create those structures. Okay, so first thing we are going to be talking about is nitrogen solubility index. Essentially, this talks about the denaturation of protein, and you can see that post extrusion. So let's just talk about uh, the raw. So with pre-extrusion nitrogen solubility indexes, right? The proteins are not that denatured, pretty high, both for without gluten and with wheat gluten. But once you do your extrusion, again, for without wheat gluten, you don't see much of decrease in the nitrogen solubility index, which is an indicator of your texturization, which means that the product hasn't really texturized a lot. But when it comes to, as soon as you add wheat gluten, you can see that texturization happening, which you can see by a drop in the nitrogen solubility index. The drop is good, like there's a good enough drop in low moisture meat analog, but there is a further drop in high moisture meat analog. So this kind of shows that wheat gluten is important in texturization, and high moisture meat extrusion is actually giving you a better texturization than low moisture. Okay, so this is the second graph is on integrity index, and essentially what this is showing is how easily does your sample break. And you can see that as soon as you add wheat gluten, you just have much more structural integrity to your samples, which is what you want. Again, you don't want too much integrity. And again, this paper has not really compared to what is the textural integrity of a meat product, but then you can get an idea. And that is why a lot of people, manufacturers add at least some amount of wheat gluten because it gives that sort of structure to your product, which you want to see in a meat-like product. So this again talks about the springiness and hardness of your final extrudates. So this slide talks about springiness, and what it really shows here is the springiness of your product immediately post extrusion, 15 minutes post extrusion, and 30 minutes post extrusion. And you can see that without wheat gluten, that thing really drops. Your springiness drops, which is something you don't want, right? You want your product to be some amount of springy and give that resilience to your bite, which is there in a meat-like product. And it is much more evident in a low moisture extrudate product versus in a high moisture extrudate product. So really, again, the takeaway being that wheat gluten is helping the product retain its structural integrity, and more so in a high moisture meat analog product. Same thing with hardness. Again, we can see the same trend, though there is a significant drop even with the addition of wheat gluten and in high moisture extrusion cooking. But then again, the same trend holds true that without wheat gluten, it drops much faster. Here is a good, few good images to kind of visualize the kind of products that were analyzed. So product A is without wheat gluten at 150 RPM. Product B is without wheat gluten at 200 RPM. C and D are with wheat gluten again at 150 and 200 RPM. Uh, a thing to note is that between 150 and 200 RPM there is not much of a difference in both, and this is the case throughout, right? Like we looked at the springiness, we looked at the hardness, we looked at the texturization indicator, etc., and we really didn't see much of a difference between the screw speed and how they affect the product. Again, to all the listeners over here, this is again with this particular study, but if you execute your own extrusion process, you can see differences. So you basically need to validate it for your own protein, for your own process, etc. But then you can see that as soon as you add wheat gluten, you see like this good layered sort of structure, which is what you're used to seeing in meat-like product. And that is why people usually add wheat gluten to their formulation. And now this is high moisture extrusion products. Again, A is without wheat gluten at 150 RPM, without B is without wheat gluten at 200 RPM. C and D are with added wheat gluten at 150 and 200 RPM. Again, no difference really between by changing screw speeds in both the categories. But you can see that as soon as you add wheat gluten, you just see more of these fibers, which is always a good thing. And this is a good kind of schematic showing what is happening to your protein. And this is what I was talking about earlier, right? When you add your protein isolate in the feed section, the proteins are globular in nature. But then post that, as soon as they go through like different barrels having different temperature and pressure conditions, they start opening up. And finally, when they exit the die, if it is a low moisture extrusion technology, you know, because they are going from a high pressure to a low pressure system, they kind of open up, they expand, air comes in, and you see a lot of air bubbles in them. And that is why, and they dry, right? So, and that is why you see that they need to be rehydrated there. You can see the air bubble structure. The structure is very different. But whereas with high moisture extrusion technology, they are directed into a cooling die, which kind of aligns all these fibers. And if you can really look closely at the schematic, you can see all these fibers actually joining at some point, and much less air cells in them, which is what gives them a really good fiber-like structure. So that was an extrusion. Let's move on to another technology called shear cell technology. And shear cell technology is basically being developed at Wageningen University in the Netherlands. So you can look up Wageningen University shear cell technology and learn more about it. The name of the professor is Professor van der Koot, and he's an expert in this technology. And what really happens is in an extruder, you are always limited by the die size. So your product can never be as thick as you want it to be. I mean, for certain applications. So that's when shear cell technology came in, wherein you can have chunks of product instead of blocks of product. There are two ways of going about shear cell technology. One is the cone and cone configuration, and another is the cylinder and cylinder configuration. And again, it essentially talks about the same aligning, right? You treat it under various temperature and pressure conditions, and again, the fibers get aligned, and you get your final product, which is texturized. And here are a few examples that are shown of texturization. So you can again see the same extrusion like strands, but you can see them, they have they could have much higher thickness. 3D printing is another interesting technology. Again, this was, I think, there's a company called Novameat based in Spain, which is working to commercialize this technology. But in addition to Novameat, there are also other companies coming up around the globe again who are printing their steaks or printing their chicken. And I think what you can see at the bottom of your screen is a 3D printed steak, and it's not animal-based steak. Oh yeah, so this is redefined meat. It is again based in Israel, and again they are making 3D printed steaks, roasts, and stew chunks. And essentially, the process used over here is micro extrusion 3D bioprinting. So essentially, your ink, what you say, are essentially is a combination of proteins and carbohydrates and fats, etc. And then you have an automated CAD program which has defined the kind of structures and kind of layers you want in your product, and it does that, and then essentially you cook the product after this. Spinning is another interesting technology, which is being used by a couple of companies now to get these fibers. So here is a company called Cybercolloids. Again, I believe it is based out of United Kingdom, and you can see that they have got this fiber-like structure. It resembles like a minced or a restructured meat product, but not using extrusion, but using a spinning technology. Essentially, the way they do this is it's very simple if you think about it. They take soy protein isolate and they solubilize it. They put it in an alkali solution, so at a pH of 12 to 13. And then what happens is it dissolves, but it's also denaturing at the same time, and the viscosity is increasing. Then they pump it through a spinneret. So like there's really small holes, but when they pump it into an acid bath with a very low pH. So what happens at this point is, in a combination of denaturation and also the protein kind of like salting out, because it's at some point passes through its isoelectric point, it comes out in the form of fibers, and that's how you see it. And you get these fibers, and you can collect these fibers, stretch them, wash them to remove the salt and acid, and then you can either collate them together or blend them with fats, binders, colorants to make your final plant-based meat product. Freeze texturization is another technology that is being used to create the sort of fiber-like structure, as you can see in tofu. And you can try this as home too. You can like freeze thaw your tofu and then see how the texture changes. And essentially, it's a play of ice crystals, formation of ice crystals and then breakage of ice crystals, and it gives this texture. In addition to this, people are using, and I believe this was a question in yesterday's session, people are using natural sources to creating plant-based meat products instead of using different technologies as we discussed. So jackfruit, which inherently has this sort of fiber-like texture, or mushrooms, which have these fiber-like texture and also the umami flavor, or seitan. So something very interesting, and if you are working on using any of these natural sources to create plant-based meat products, again, you can find literature and companies working on this too. So moving on to restructured versus whole muscle products, and this is what we were discussing, right? Your keema-like products are more like restructured products, whereas your whole muscle products are your more chicken breast, chicken thigh-like products. This is kind of just saying the same thing, what they resemble. And typically restructured products, you don't need to have high moisture meat analogs for this. If you have like really functional low moisture extrudates, you can still use them. And because people are not really looking at the texture, right? I mean, till you have a good macro texture and a good flavor, you still have a good product. And here is a flowchart which actually talks about how do you make a final restructured plant-based meat product. And as I was just saying, typically you can use a TVP, and then you hydrate it with water, broth, fats. Once the hydration step is done, you blend it with any other protein or flavors or any functional additives, and then you essentially mix them together, form a dough, and then you form them in patties or nuggets or sausages. Post that, you can coat them, so you can use a lot of breading, batter, etc. And then you can either cook them by various methods, and then it becomes your ready to eat product, or you can just pack them at this point, and that becomes your ready to cook product. In countries like India, where supply chain is not necessarily frozen supply chain or refrigerated supply chain doesn't really exist, you can subject it to extended shelf life processing, Retorting is commonly used by companies in India, and you can look at good dot. A lot of their products are retorted so that they are shelf stable. And then essentially post that, cooling is mentioned over here because a lot of times in countries in the West, frozen and refrigerated supply chains exist. So you could even freeze them after that, and then you package it and store it. Whole muscle meat products, again, they resemble whole muscle cuts of animals, and they actually display the fibrous texture similar to a striated muscle. In terms of making it, we have mentioned that you could use a TVP in this, but typically wet moisture extrudate is used to make a whole muscle plant-based meat product. And think about the video, like the Coperion video, once you get the wet moisture or high moisture extrudate, it is typically marinated, with any flavors, fats, or functional additives. Post that, it is coated if you want it with any breading or seasoning, etc. And then you can cook it. Like you could boil it, bake it, fry it, etc. And then you could subject it to extended shelf life processes again, and then cool it, and then package it and store it or sell it. So really, when you're making a plant-based meat product, be it restructured or be it whole muscle product, you need to make sure that you are getting three grounds right. The first ground is sensory and appearance. Your consumer is used to seeing, their plant-based meat product in a certain format. Like, so you need to have the fibrous muscle-like texture. So if you are eating a chicken kebab, when you're biting into the kebab, and then typically the consumer does see or feel the product, right? It has that muscle striata, so it needs to be that. If you're making a plant-based chicken kebab, it needs to be juicy, and it needs to also have the right flavor. In terms of functionality, again, it needs to be functional in a gravy like application, in a baking application, in just grilling application, frying application, etc. So you need to make your product versatile too, because really your consumer can use it in a lot of ways. Or otherwise you need to really specify it on your packaging that this can be used only for grilling and nothing else. But then again, that becomes sort of the weakness of your product. And then nutrition, a lot of people actually consume plant-based meat because it's a quality source of protein. So you need to think about how you're going to be making it as nutritious as its animal-based analog, good source of calories, and also good source of vitamins and minerals. Uh, so then talking about nutrition, which we just discussed, plant-based meat can be formulated, and this has been shown by companies like Impossible and Beyond, to be the same nutritionally as animal-based meat or even better. So if you really look at, and this is taken from Impossible's website too, they compared that Impossible burger versus an 80/20 beef burger, and they found that, so let me switch my pointer on. Okay, so if you look at this, if you look at the protein, where's the protein? So both the products have 19 grams of proteins, but if you look at the Impossible Burger, it has fewer calories, so just 240 versus 290. It has lesser fat, less saturated fat too. It has more fiber, so 3 versus 0, more vitamins and more minerals. Sometimes plant-based meat products get a flag that they are high in sodium, and even here you can see they are high in sodium. But you need to think that this is a final ready-to-eat product. Essentially, you just need, sorry, ready-to-cook product. So you just need to cook it, put it in a burger, and eat it. But whereas with a beef sort of patty, it's not at all seasoned. So you are going to be adding salt and pepper and stuff. So your sodium is going to increase. So that's not a fair comparison. Now, when it talks about proteins, right? 19 grams of protein versus 19 grams of protein, in terms of quantity, they might be similar, but not in terms of quality. So, protein quality is a term which basically talks about if that protein has all the essential amino acids in it, and secondly, how digestible are those amino acids. And essentially, there are different ways of classifying protein or determining protein quality. One method is the protein digestibility corrected amino acid score, which is PDCAS. And then the second is the digestible indispensable amino acid score, which is DAS. People are nowadays moving from PDCAS to DAS because it is slightly more accurate. So you can read up about this. There's a lot of literature. And essentially, as you can see, casein, which is a milk protein, and egg white, these have a PDCAS values of 1. So which shows that they are really good proteins, and even beef has 0.92. Whereas if you look at plant-based proteins, they are low. Like, look at whole wheat, it is 0.42. Wheat gluten is 0.25. Sorghum, maize, they are between 0.2 to 0.3. Soy protein concentrate is pretty good, 1. That is why, again, people use a lot of soy. But then again, you can see that you can actually blend different plant proteins together and increase your PDCAS value. So that's why a lot of companies use blends of protein isolates, because using that they can make the protein quality similar to animal based products in addition to protein quantity. Micronutrients, again, as you saw, impossible. You can fortify your product with vitamins and minerals, which is great. And some countries like Canada actually require plant-based meats to be fortified, so you cannot sell a product in Canada calling it plant-based meat if it doesn't have a certain amount of macro and micronutrients. Okay, so I think we'll stop here, and I can take questions because we are essentially done with the extrusion with the texturization component, and the next part is just going to be talking about different white space opportunities.
Awesome. So I'll take a couple of questions. How do you think, like, what are your thoughts about the idea of optimizing, different proteins for extrusion, like that as a business? It's kind of vague, but and you've talked enough about the opportunity areas of why that is very important, optimizing protein sources before they go into extrusion. Maybe just key pointers there.
Sorry, can you repeat that question? Like optimizing, so what parameters should I be using in extrusion to give my product an edge? Is that the question?
Yeah. So kind of so if somebody gives us a specific focus on optimizing protein ingredients, the sources of protein for extrusion, then just some key level insights on that.
So again, my answer is going to be like a lot of parameters, right? Like till now, if you can see, a lot of people have just worked on soy or wheat or pea protein. But if you have a novel plant-based ingredient, who knows? I mean, you extrude it and you might get final texture which is very similar to a plant-based meat product. So that is something that can give you an edge. You can also work with working with conditions, changing your extrusion conditions a lot. And again, this is a very big question, right? Because I can't really tell you that increase your temperature or decrease your temperature, because you would want to do that based on the protein source that you're using, uh, and the final product quality that you want. So really, you could look at this material, go back to the different parameters that you can use to kind of change the final product quality, and then do something that would give you the best product quality.
Thanks, Siddharth. I think the next question is the effect of extrusion on protein, star, sugars. That is something we learned today, and people in general know about that. What about other equipments that are usually used for processing in other categories as well? How much of distortion or destruction of such structures do we see in other equipments, or is it more intensive in extrusion? Just comparables there.
Yeah, so extrusion is a pretty intense process if you look at it, right? And you saw in the videos too, it really, it's going to denature your proteins. Your material is going to be subjected to temperature, pressure, shear at the same time. If you look at shear cell technology, also it's the same thing. The configuration is different. Uh, well, slightly less. You can find some papers which do say that you have much more control over your material and the way it is being texturized versus in an extruder, because it has so many variables. It's difficult when it comes to spinning. As you saw that it is a different kind of stress to your material, not so much of temperature but more of acid based stresses, and that's how your protein denatures. Yeah, so again, extrusion is definitely on the higher side of things that you could do to your raw material, like in terms of temperature, pressure, and shear.
Awesome. Well, I'll answer the next question. Why hasn't 3D printing become the new normal or the new norm? Um, the feasibility is obviously one big factor, and industries are not created over a couple of years or 3 years. Extruders and manufacturers of extruders, like we have a very interesting webinar on 18th, like I said in the last session as well, with Wenger Manufacturing Incorporated, which is one of the largest manufacturers of extruders for this sector globally. And so industries and the way supply chains and different actors, different companies, that they create different technologies and then they actually scale up, they put millions of dollars together as an industry towards improving a technology, right? They employ people to study different parameters, they optimize it. And this has been done for a longer time, much longer time for extruders compared to 3D printers. Eventually, when more people focus on 3D printing, like we have a excellent 3D printing facility in Vishakhapatnam, you know, in Bio Valley, but they are currently using it for a lot of different purposes, other materials, not for food grade materials. But such world class facilities are becoming more and more the norm in other countries as well, and that gives a scale. Once that scale has reached and economies of scale really come through, then a technology becomes the new normal. So currently it is in the development and research stage, right? Not just for plant-based meat, for n number of other things as well, for n number of other foods. So that's definitely growing up, but it's not become the new normal because of these reasons. Anything else technically to add here, Siddharth?
No, I think I agree with you, Shardul. In industry and academia, they kind of collaborate to build. So if you just look at extrusion, right, and low moisture extrusion or even high moisture extrusion now, uh, there are a lot of research papers that you can find, which industry can refer to and kind of build up on them. But if you look at 3D printing, again, there has been a lot of research on 3D printing in other fields, but not really the food field. So you might struggle to find a lot of examples of 3D printing being used for like plant-based meat creation or something like that. So yeah, so science is developing, the economics of scale are developing, and all this together will make 3D printing viable in a few years.
Yeah, Nova Meats is a global pioneer in 3D printing in many ways, in terms of being a startup. So look it up. Giuseppe Sionti is the founder of that startup, and they exclusively focus on 3D printing for plant-based meat. Somebody in the comments mentioned that IFPT Thanjavur recently also introduced 3D printing facility for food. Niftam, I think, had a 3D printer during my time back in 2016 as well. So people definitely have some research going on in the food category on 3D printers. But like Siddharth said, you'll have to really dig deep and probably connect with the right people if you want to understand this and how they're using it. Again, it would be similar, right? It would be about optimizing parameters. There would be possibly a different angle to achieving the same kind of shear or force, or it might just be used to use a kind of base material and structure it a little better. So that's why whole cuts which are needed um, in the West, like steak, etc., are made through 3D printing. And in India, we'll have demand for those steaks for specific cuts as well, right? In a lot of dishes that India consumes, we have very intricate structures that could possibly be printed via 3D printing, and then that might become the new normal in the future. So just something I wanted to add. Um, Siddharth, just take a look at the Q&A section, and we'll go starting with top. Um, about fortification, at what stage should the fortification be done? I mean, in keeping in line extrusion and some other processes that you mentioned.
Uh, so again, extrusion is a pretty intensive process with high temperature and stuff, and as you all know, like vitamins are heat sensitive. So if you can add it towards the end of the process, that would be good. And again, when we showed the impossible slides, they have that low moisture extrudates, and then post that, they are adding everything as a form of a slurry. So you could check that. I mean, I think that it would be an advantage to add at some later stage of the process to avoid processing losses.
Yeah, thanks. The next question is about the necessity of gluten, wheat
Wheat
gluten.
gluten.
Yeah, so that question.
Yeah, this is a good question, right? The person is right that when it comes to seafood, uh, you know, where the structures, it's more flaky than like proper layers and for proper fibrosity. Maybe wheat gluten is not needed, and this is something that just like repeated experimental trials can prove. Uh, yeah, but this is a great idea. I mean, a lot of people don't really want gluten in their product, and if you're making seafood, maybe gluten is not necessary.
Awesome. So mixing two kind of protein sources, let's just say faba and quinoa or wheat gluten, um, how do we really try to gauge in the specific context of this challenge as well through ideating while you're not actually doing research? What are some key things to keep in mind where ingredients might end up with a negative impact on the end product? Like, are there any no categories of mixing? Anti-nutrients is obviously something you should think of, but in this case, just some general guidelines that how would you think about ingredients and their mixing properties?
Yeah, so I would say that, if you're still in the phase where you want to decide which proteins should I use in an extruder, you can look at functional properties, right? Again, few of the functional properties that you want to target are good emulsification capacity, good water holding capacity, good structure building capacity. So based on that, you could decide which proteins you want to add in the extruder. Now, when it comes to, like, if I add one type of protein, will it kind of counteract the effects of my other type of protein? This is a very complex question, because again, with the change in temperature, your protein is in different sort of it has a different structure, right? Because it's in the form of it's denaturing and stuff. So this all of this can be figured out only through experimental trials.
Got it. And the next question talks about jackfruit and how it is very less in content of protein, but it gives the structure, which is fibrous, which is meaty. So, have you seen any examples where jackfruit was blended with legumes and pulses to increase the protein content and functionality in the end product?
So again, as far as I know, you can't really. So jackfruit is in its just like native form. It is very like fibrous and stuff. And most of the people who are using jackfruit to create plant-based meat products, they are using it in its whole form. They are not really like crushing it and then blending it with say chickpea protein or fava bean protein and then extruding it. So it's a different use case altogether. And I know that it is low in protein, but then again, protein won't be the USP of your product there, right? You might want to sell it as, clean processed or clean label because you have not used any protein isolates and stuff. So it's just a different USP.
Yep. Thanks. Um, are we saying when we are talking about macro and micro structures, are we saying that microstructures are not very important to mimic as long as we have significant or at least satisfactory replication of macrostructure?
So this is again an interesting question, right? In the end, when I'm going to be having a product, or when any consumer is going to be having a product, for them, texture is texture, right? Like either, if I'm able to get the macro structure right, and that is giving me the kind of texture I need, or if it is like, you also have the microstructure, you know which is giving the final product texture. So consumer is not going to see that. So what I'm trying to say is that if you look at meat science again 101, you'll see that meat, the fibers what you see, that's not one fiber. Each fiber is a blend of like hundreds of fibers inside it. So it really depends on what you would like to achieve. Now ideally, if you ideally you should get the right texture right from the microstructure point to the macrostructure point. But then again, that would be an R&D intensive process. I don't even know if it would be possible or not possible. But then if you are getting macro structures right, which is what extrusion is doing, and you're still getting a good enough texture, maybe that is good enough, at least to begin with. Or you could use spinning technology, right? And then see how you could blend all of these fibers together into intermediate macro structures and then blend them to get the final macro structure. So uh, it's a very interesting question. Maybe there are research papers which talk about this, and I would ask the person to take a look at it. At least, like, I don't know a better way to answer this further. So
Yeah, but I think that
I
that
could,
kind of
yeah,
context makes sense. Yeah,
yeah.
and certainly that would give them a better idea about how to think about it. So there was a question around wheat and soy. Though they contain allergens, they're still widely used across the industry, even in our sector. Why is it that? Is it because their functionality is more when compared, I mean, the value that their functionality brings, is it more compared to their allergenicity and, those aspects?
So it's a combination of a lot of things, right? Again, soy and wheat protein isolate is something that is available everywhere and for a much cheaper cost than any other protein isolate. So people want to use novel proteins, but then if I tell you that you could buy a kg of soy protein isolate for 50 rupees and a kg of mung bean protein isolate for 500 rupees, then it just works better with cost economics. Secondly, soy protein has been worked on for decades to kind of optimize it, uh, and you could reach out to ingredient suppliers and be like, I want a soy protein isolate which texturizes really well, and they'll have that SKU for you. Uh, so that's that. Yeah, so again, as Shardul was mentioning, right, it's about an industry developing. Like you could do some lab scale experiments and say that, hey, power beam protein isolate works the best in an extrusion. But how do you even make it? Like, you would have to make that, for which you need to have your back-end supply chain established. You need to have contract farming done with farmers who actually create this power beam. Then you need to have, processing facilities which know how to process power beans into protein isolates. So it's just, when you're starting off, you want to focus on one aspect of the product, and that's why people usually go with something that is available out there, optimized, and then they kind of invest in building their own novel ingredients.
Yeah, so we are not talking about just the ideation phase right now, right? Not just the proposal. In general, if you're an entrepreneur who's resource constrained and wants to work in this sector, you're obviously going to think about the most practical, feasible, cost-effective ways of getting things done. So it's there's no point in thinking about oats as an ingredient for a couple of years and then figuring out, hey, India doesn't grow enough oats. I'll have to import them or the protein from them. So those factors you have to really keep in mind throughout your designing of your company. So all of those things are super important, and the same example is also true for 3D printed meats, like we're discussing that technology. So ingredients, technology, talent, it's also valid for talent, right? Not enough people understand this sector. How would people, uh, stakeholders in the community would hire talent, sci-tech talent, because they have never been exposed. That's why I think this challenge in phase one, phase two, you really understanding all of it and really taking the time to study it would really help your careers in the long run. Most of you who are taking it seriously. So that's just an addition to that simple analogy. Um, I think we can get started with the session, Siddharth. Now, enough questions for the time being, and we can get back to questions at the later part of the session.
Okay, sounds good. Okay, are you guys able to see my screen? Shardul, can you guys see my screen?
Yes.
Okay, perfect. So, in terms of white space opportunities, what you see on the screen is like the entire value chain, right? Of end-to-end sort of in making a plant-based meat product. So, as we discussed, you start off with selecting the right crop, growing the right crop, setting up the right sort of back-end supply chain for it. Maybe you could also work with universities or do some in-house research to breed the crops to kind of improve the protein profile or to improve the functionality, etc. Post that, you use different processing methods to isolate the components that you really need. Post that, you actually use extrusion, shear cell to create these texturized materials what you need. But that is not it. Then you kind of hit your manufacturing stage, right? And again, from experience, I can tell you that you could develop products on lab scale, but then manufacturing is a whole new ball game. You'll suddenly realize that, like one example which I told you, right? You'll realize that, hey, this feeder is actually not feeding in my materials, right? Because the density is off and stuff like that. And then you have to modify the process, and you just lose a lot of time and batches, etc. in this process. So you always need to account for that. Again, you'll see that the flavor, color, and texture of your product is very different from what you developed on at lab scale. So you need to again, optimize it further. Safety, QA, and regulatory. What you're selling needs to be food safe. Any one food safety incident and your brand is like completely gone. So you need to make sure that your product doesn't have any pathogenic microbes, spoilage microbes, etc. You need to have the right quality assurance practices in place. If you're developing any novel ingredients, you also need to have the right sort of regulatory approvals before selling your product. Post that, you need to understand how would you brand and market your product, right? So again, falling back on another question that was asked earlier, if I'm developing a jackfruit based product, maybe I don't want to call it a high protein product, right? I want to focus on like a clean label, clean processing type of branding marketing, versus if I'm making a product which is a blend of different proteins such that it is a complete protein, then I say that, hey, my protein quality and quantity are similar to me. So this is also a big thing. It can like really make or break your product, the way it is marketed and branded. Financing and business services. An extruder can R&D scale extruder, from European companies which are state of the art, can cost you 6 crores, and a manufacturing extruder can cost you anywhere from 15 to 20 crores, and that is just the extruder cost. So you can imagine how much cost would go into R&D, setting up of a facility, etc., etc. So you need constant support from investors to kind of help you in financing your business. End products, new product lines. Do you want a kebab product? Do you want a gravy product? Do you want something else? Sausage, patties, etc. So you need to keep determining that and change your entire value chain accordingly. Brokerage and distribution. Fine, you made a ton of chicken tikka. What do you do after that? You need to have the right cold storage places or the right warehouse facilities. You need to have the right distribution system for your product to go from point A to point B, C, D, E, and F. You need to decide if your product is going into food service or if is it going into retail, and accordingly change your pricing, change your packaging, etc. So here is just, kind of just deep diving into what I was just mentioning when it comes to crop characterization. Few white space examples is, crop breeding for plant-based meat optimization. And this is something we touched upon in our first session too last week. So, you could actually be a company which, does exclusively plant breeding, right? So you could say that, hey, I'm going to make a soy protein isolate, or I'm going to make a mung bean protein isolate, which is a really good emulsifier, and that's what my company is going to do. So my end product is going to be this highly functional mung bean protein isolate or a fava bean protein isolate, and you could supply it to plant-based meat companies, and they can make products from it. In terms of ingredient processing, again, you have your protein that you're extracting, but if can you find ways of using your fiber and starches and fats, etc., so that you could get your cost down of your actual protein that you need. Production methods, again, high moisture extrusion is great, but can you optimize spinning technology? Can you optimize pre-texturization, etc.? Is something to think about. Branding and marketing, again, how do you, this is essentially what I was talking about, your category marketing, in-store demos, how could you make your consumers more aware of what your company is doing, what your product is capable of? Safety, QA, and regulatory, again, you need to have the basic regulatory approvals in place like FSSAI, etc. But in addition to that, if you're using novel ingredients, you also need to get it approved. Product development is something we just spoke about. Manufacturing, do you want to have a manufacturing facility in-house? Do you want to contract it to co-manufacturers? Is something you need to decide. Again, financing is the same thing. There are different ways of going about financing. You could have your own personal funds or family funds, or you could go through the VC route, etc. And product lines, again, need to decide what do you really want to make. When you say I want to make a plant-based meat product, a lot of times, that's a very high level answer. What do you really want to make in it? And can you make that product is something that you need to decide. Brokerage and distribution, again, how do you get it through the right channels with the right cost economics? I wanted to highlight this again. GFI, we